Light interference is difficult to create and observe. Thomas Young created two coherent sources by splitting light wave from a single source, which is the sun. It can be observed by placing the screen relatively far away from the source. When we say coherent, it means waves are in phase or have a definite phase relationship. When we place two slits, it provides two coherent light sources that then interfere constructively or destructively. Young used sunlight where each wavelength forms its own pattern, making the effect more difficult to see. The positions of maximum intensity on the screen is where the antinodal lines intersect. To calculate the maximum intensity of the screen, we have Y max is equal to R times tan theta M is equal to M lambda over D times 1 over the square root of 1 minus M lambda over D squared, where R is the distance on the screen, D is the separation of slits, and lambda is the wavelength, and M is the order of the fringe. To also calculate the positions of minimum intensity on the screen where the nodal line intersects, we have gamma minimum is equal to R times tan theta M is equal to M plus 1/2 times lambda times R over D times 1 over the square root of 1 minus M plus 1/2 times. So if M lambda over D is less than 1, we can have this formula for the maximum intensity of the screen. Gamma max is equal to M times lambda times R over D, and we can also have this formula to calculate the minimum intensity of the screen. We have gamma minimum is equal to M plus 1/2 times lambda times R over D. Figure 1 shows Young's double-slit experiment with geometric analysis. In Figure 1a is the interference of light waves passing through two slits. Young creates two coherent sources by splitting light wave from a single source. In the first slit, it creates cylindrical wave fronts, and in the second slit, it creates coherent wave fronts. As you can see, the screen are relatively far away from the source because it can only be observed if we place the screen far away from the source. As it passes through, it produces bright bands where wave fronts arrive in phase and interfere constructively, and it also produces dark bands where wave fronts arrive out on phase and interfere destructively. In Figure 1b, it is the geometric analysis of the light waves passing through two slits. The first picture shows the actual geometry seen from the side, and in reality, the distance of the screen is usually very much greater than the distance between the slits. Figure 1c shows the approximate geometry of light waves passing through two slits. Through analyzing this, we can treat the rays as parallel, in which case the path length difference is simply the distance from the screen 2 minus the distance from the screen 1 is equal to the separation of the slit times sine. So the linear dimension of the separation of borders obviously depends on the angle and the distance from the screen. If it's far away from the source, it can be observed. So here we have R is the distance to screen, D is the separation of slits, and M is the order of the fringe. In the left side, we have the M, or the constructive interference bright regions. So at the bright regions, we have the origin of 0. When it goes up, it measures the positive, and when it goes down, it measures negative. So in the dark regions, it has the origin of 1/2, and when it goes up, it measures positive, and when it goes down, it measures negative. So let's try this example 35.1. Given the measurements in the figure, what is the wavelength of the light? To solve the wavelength of the light, we need to derive from the formula gamma max is equal to m times wavelength times r over d. So to get the formula for wavelength, you need to multiply the formula. And cross multiplying, you can get m times lambda times r is equal to y max times d. In order to get the wavelength, you need to divide both sides by m and r. So the formula in getting our wavelength is equal to y max times d over mr. So after that, you need to substitute the given numbers, value to the formula. So we have 0.00949 meter times 0.002 meter over 3 times 1.00 meter. So we can get 0.000019898 over 3. So our wavelength is equal to 6.327 times 10 raised to the power of negative 7 meter. Let's solve another problem solving. In a two-slit interference experiment, a beam of light with wavelength 600 nanometer is directed through two narrow slits separated by a distance d is equal to 0.1 millimeter. The interference pattern is observed on a screen placed 2 meters away from the slits. Calculate the number of antinodal lines created by the interference pattern and the distance between successive maxima on the screen. First, you need to get the number of antinodal lines, the maximum possible m that can be at antinodes is given by m max is equal to interference times d over lambda, where d is the slit separation and lambda is the wavelength of the light. So substitute the given values. M max is equal to interference times 0.1 mm, which is RD, over the 600 nanometer. So we have M max is equal to interference times 166.67. So there are approximate 166 antinodal lines created by the interference pattern. Second, we need to get the distance between successive maxima. So the distance between successive maxima on the screen can be calculated using the formula change of gamma is equal to change of max times d over mr, where change in gamma is the distance between successive maxima and the gamma max is the distance from the central maximum to the first maximum. D is the slit separation, M is the order of the maximum, and R is the distance from the slits to the screen. Given that R is equal to 2M, gamma max can be approximated as D is I over 2, and for central fringe, we can approximate M is equal to 1. So substitute the given values. We have change in gamma is equal to 0.1 millimeter over 2 times 0.01 millimeter over 600 nanometer times 2 meter. So we can have change in gamma is equal to 0.05 millimeter times 0.1667 times 2 meter. So our change in gamma is equal to 0.0167 meters. So the distance between the successive maxima on the screen is approximately 0.0167 meters. That's all. Thank you.